So hi everyone, welcome to another edition of NLP with Friends. Today I'm super excited that we have Sherry Wu with us, who is a fifth year PhD student at the University of Washington, co-advised by Jeffrey here and Daniel Weld. Sherry's research focuses on helping humans more effectively and systematically evaluate and interact with their models through HCI and NLP. Yeah, so we'll hand it over to her in a minute. So Sherry has very kindly agreed to take questions during the talk. So you can feel free to unmute and ask your question or use the raise hand functionality in Zoom and we will call on you. For questions at the end of the talk, you can ask them through Dory. I've just posted the link on the chat, but it's also in the emails that you've received earlier. So if you can ask your question non-anonymously on Dory, it's kind of better because then we can call on you and have a conversation. But if you want to ask your question anonymously, that's also totally fine. Okay, so I think that's it. Over to Sherry.
Let me share screen. I guess you can see the screen. Give me 1 minute. Let me open chat and also participants window so that if people really wanted to ask questions during the talk, please feel free to either type in the chat or raise your hand. Hopefully I will see. And if not, feel free to cut me off. I'm always happy to take questions. So yeah, thank you so much for having me here. And yeah, so like they have mentioned, I work on the intersection of HCI and NLP, and today I'm going to talk about principles and interactive tools for evaluating and improving the behaviors of NLP models. It's a really fancy name, and I will talk about multiple work that's spread across all of my PhD progress. But essentially, this talk is just about building some tools and structuring our unstructured text data so that we understand our NLP models better. Cool. Let's say I'm a researcher and I come up with a new model and I write a paper and I call it Oscar. How do I know if it's really working? And if Oscar is a question answering system, should I just go ahead and replace my doctor with Oscar? Or maybe I work at a company like Microsoft. Then we have to decide if we should go ahead and use Oscar in all of our products. And if it's not ready for product, what should we change about the model? The most common way for us to evaluate our model is to use some standard metrics like accuracy or F1. If people know some of the very famous NLP benchmark datasets like GLUE, you would see there are many models that have already surpassed the human accuracy. Let's say Oscar is just like this. It beats all of the baselines and all of the standard benchmarks. Is this enough? Of course not. Our evaluation does not always reflect the actual capabilities of the model that we built, and our NLP models can be accurate but still have a lot of weird behaviors. One problem could be it looks so nice overall, except for some very specific types of data. Maybe because of how we collect our training data, our model is biased towards certain populations. For example, when you ask a model to describe what is in an image, it deals with this kind of 3 examples from the test set perfectly. It sounds pretty cool. If we are just computing accuracy, we will conclude that my model is pretty reasonable and call it a day. But if we just find another image from the internet, we will quickly recognize that the model cannot deal with bedding costumes from a different culture. And the pretty accuracy score was just because our test data has the same kind of bias as our training data and would focus more on the Western beddings. So our problems become, how do we know that our model is not striving for perfect performance in the majority group by sacrificing their support on low resource groups? And another problem with your model could be it is right for the wrong reason. So as a visual question answering model, what is this mustache made of? The model would say banana. Again, the model looks pretty good up until now, But if we dig just a little bit deeper, we will see it will still answer banana to what are the eyes made of, and it cannot let go banana even if our question is not even complete. And this is because the model would overfit to this what question and automatically just search for the most salient object in the image. So our second problem is, how can we confidently say that our model is not relying on some superficial features? If you're analyzing structured data, we are curious about a data slice, then we can just say, let's do a group by and then call it a day. And similarly, if we want to know whether the model has learned about a particular feature column, we can just edit it and see how our model reacts. But for text data, we usually don't have a good specific feature or column to slice on. What's our workaround to avoid this difficulty? If we read either some dataset description papers or some model error analysis sections in the NLP papers nowadays, they actually have some shared universal methods. Like we sample 20 questions and then manually analyze them. We randomly select some instances and categorize them. And really, it's just different ways of saying, take a random sample of the data and manually categorize them based on what we guess to be the important features or important similarities. This is a pretty easy process, but it's not reliable. Without actually testing on the entire data, our subsample may not correctly represent the data set, and our manual categorization can be pretty subjective, and we may even be trapped by some non-generalizable or local patterns. So this is where I try to jump in. For the past several years, I try to uncover some pitfalls in the status quo analysis process, which are some of the focus of the papers I mentioned in the previous slides. And I also try to help NLP practitioners, people like you, to inspect the inputs and outputs of the models such that practitioners can gain some more systematic insights into their model behaviors. And I will focus on this in this talk. In other words, if we consider these 3 big steps before we actually deploy a model, I focus on these 2, and I expect the understanding will eventually help us train better models. In response to the 2 problems hidden in the accurate models, I work on 2 building blocks. First, to verify model performance on data slices, I explore grouping methods that would quantitatively find a collection of similar text instances, and the similarity could be from a semantic or a synthetic perspective. And second, to isolate the effect of certain patterns, I work on counterfactual perturbations to help make targeted minimum rewrites on sentences. I instantiate these 2 building blocks for different analysis stages, including model error analysis, explanation, and behavioral testing, which is more on the output side, and also dataset assessment and augmentation, which is more on the input side. Throughout the way, I also explore how to balance the machine power and human intelligence for different stages. Like these tools mostly have interactive methods for NLP people to input their domain expertise, but also they would take the machine power to become more scalable and try to prioritize some data set or task properties when human alone is pretty biased. And in the future work or in ongoing work, I also plan to extend those 2 building blocks to data collection rather than just analyzing the inputs and outputs of already collected data. So let's dive into some more concrete work. First one I will talk about is Erudite. Erudite is a tool for error analysis, and it has an interactive interface which shows us high-level model performance summaries and a list of individual instances and some other analysis panels that we will reach later. The goal of this tool is to help people better understand why the model makes certain mistakes. Erudite is the work that sets the tone. I first concretized these 2 building blocks in this work. So the other projects I will talk about later will just be enriching the design of these 2. And I will give you a walkthrough example, hopefully to convince you that the two building blocks here are important for precise, scalable, and testable error analysis. So the walkthrough will be question answering. Given a question and a context paragraph, the model is supposed to find a text snippet or a span from the context to correctly answer the question. And our focus is on a model called BiDef, which is a pretty standard and well-recognized baseline model in the field at the time when we wrote Erudite, and we ran it on Squad, again, a very standard data set when we published this paper. So what we call as distractor hypothesis is describing that BiDef is pretty good at matching questions to entity types. When you ask a who question, BiDef knows that you're asking for a person's name, but the model is often distracted by some other spans with the same entity type. Like here, instead of predicting the correct span, Marie Gold, the system returns John Dabney, which is not quite the correct answer, but still a person name. And distractor hypothesis is a common belief and was verified by quite many question answering experts in our user study. And we recreate their experience here. To know how severe the distractor error is, we first need to find all of them. We do this using a domain-specific language, or DSL. In one sentence, this DSL applies a list of pretty powerful extractors on some targets of an instance with some additional supporting operators. A very dumb case is to extract the length from the question and require it to be greater than 20. With these three components, we can quantify instances in various ways by extracting attributes from them. And filters on these attributes can then more objectively find relevant instances that all follow the same attribute pattern. And these are the 5 lines of filtering codes we write to find distractor errors. These lines here can be broken down into several semantically meaningful conditions. The first line, the ground truth should be an entity like person. Line 2 and 3, count how many ground truth entity type occur in the whole paragraph and make sure it occurs multiple times. Together with line 1, it will mean find instances that have some distractors in the context. In line 4, the prediction entity type matches the ground truth entity type. And line 1 to 4 would mean our model finds the correct entity type. Finally, the prediction is incorrect, and all of the 5 lines will get to a group of instances that are distracted. If we apply the filter, 192 instances in the group are all cases where BiDef predicts a wrong span, but the span has the same entity type as the ground truth. Notice this is already a larger number than most people can sample and inspect in their own analysis, which is like 100. It covers almost 6% of all of the BiDef errors and looks pretty convincing. Should we now go and try to fix the problem in BiDef? Well, if we apply all of the partial filters and build all of the other groups, we actually can notice a different pattern. So BiDef predicts the exact correct span 68% of the time overall, and this rises to 80% when the ground truth is an entity. And when other entities with the same type are present in the context, BiDef is still 79% accurate. And when it predicts an entity with the correct type, it's correct 88% of the time, which is actually much higher than the 68% match overall. This means BiDef actually performs better when it has distractors and the entity type is matched. So if you see this arrow and decide, oh, this is a very important thing to fix, maybe think twice, or you might miss something even bigger. So Erudite grouping gives us several benefits so far. It measures instances in a precise and quantitative way, so we can easily rerun the queries to reproduce the analysis. And it gathers instances with particular patterns, so experts could overcome this small sample size limit And it also helps us cover the entire depth set, including the correct instances. And this can give you some different conclusions compared to just looking at the mistakes. Now we've got the group related to distractors, but the presence of distractors in a wrong prediction does not necessarily indicate that the distractors was the root cause of the mistake. Back to our first example, it's easy to assume that this is wrong because of the distractor, but maybe it's because we need to do multi-sentence reasoning to link Doctor Who with the series or even something else. In Erudite, we try to help answer this question: are the 192 instances really wrong because of the distractor? By asking a related what-if question. If the predicted distractor was not there, would the model predict correctly? And we answer it with counterfactual analysis. Again, with the power of DSL, Erudite uses rules to rewrite all of the instances in a group. Going back to the question, we define a rule that rewrites the context by replacing the model predicted distractor string with this meaningless placeholder hash token, so it won't be detected as an entity anymore. Once you rewrite, we can ask the model to do the prediction again. And this is what happens with our previous running example. We've now deleted John Dabney with the red Strax rule and added the screen hash. And now the model is giving us a different distractor, which is this underlined wrong greener. And so it seems another distractor is still confusing the model. Now, if we rewrite all of the 192 instances in the is distracted group, the same change to a different incorrect entity case occurred 29% of the time. But other than this, 48% of the time, the prediction were corrected. So indeed, the distractor was causing the misprediction. For the remaining 23% of the time, the model predicts the same span, but now it contains this meaningless hash token. It's very likely that some other factors are at play then. So adding to the previous list, this kind of counterfactual analysis helps develop insights not available through just grouping. If we plot this grouping and counterfactual rewriting on this axis of machine doing it and human doing it, Erudite uses query and rewrite functions to take a mid-ground. It will help domain experts to do important downstream tasks after error analysis. And it's helpful because in error analysis, we usually already have some bias on what to inspect. However, because the query functions do rely on pure human domain knowledge, it's prone to human biases. So it's likely that we will overlook some linguistic capabilities. And to help people do some more comprehensive detection on model bugs, we designed checklists to support model behavior testing. And compared to analysis, the key of testing is that we don't have to have a model at hand or have to know where it might have bugs. All I need to know is that what capabilities we want our model to handle, and then write tests for each of the capabilities, just like how we test softwares. Before I go into checklist, do anyone have any question on Erudite? Going once, going twice. Okay, let's move on. So this checklist thing we propose contain two parts. The first one is a framework or a process that will guide people to do the testing design. And I will also talk about the paired open source tooling a little bit later. The checklist framework borrows many principles from software engineering testing. First, if you're testing a software, you typically test the individual functions with unit tests or integrations or stuff like that. With NLP, we don't have predefined individual components, but we can approximate the so-called unit with linguistic capabilities. These are generic things that occur in classic NLP pipelines, like can it understand adjectives, distinguish part of speech tags, blah, blah, blah. Don't worry if this list seems pretty abstractive. We will see some examples. One thing that's worth noticing is this list is task and model agnostic. It just includes things that show up in many different tasks. It's because at a very high level, we expect the model to deal with vocabularies and negations, whatever the task is. The task only affects how we expect the model to behave. For example, we will always need the model to know, like, the Lord of the Ring is a named entity, it's the name of a movie or a book. If you're doing sentiment analysis, the prediction should remain positive if you replace Lord of the Ring is a good movie with Harry Potter is a good movie. However, if we want to do like question answering, we would want a different answer to like, oh, who directed the Lord of the Ring and who directed Harry Potter. But of course, this is not a exhaustive list. With this being the starting point, users should be able to come up with additional capabilities that are specific to their tasks or domains if they need. Second principle we borrow is behavioral testing or black box testing. Essentially, this is saying, instead of worrying about the implementation, we just want to treat the model as the black box with some desired behavior. Really as simple as given this input, what behavior we expect on the output. And transferring to NLP, the goal is to separate the testing from model design or training. And this is good because it meets a lot of needs from the end user. When you try to sell an AI system, the user do not care its inner structure or its training data. Is it PyTorch or is it TensorFlow? They only want it to be sufficient for their use case. And it also works well with this trend of all of these black box models because you can still do testing even if you do not have access to the model structure or the training data. Checklist offers 3 testing types. So we are forming a matrix of capabilities and testing types, and the matrix will help us with this decoupling. Let's say we're testing the sentiment analysis model from Google and walk through these test types. The first one we have is what we call minimum functionality test. This is really just unit test. If we look at IMDb movie review, it's a pretty big data set with all kinds of complex and pretty entangled behaviors, trying to see if the model can follow all of the multi-hop sarcasms or negations of negations. And here we're trying to do the opposite and say, we really just want to single out the capabilities to test from other possible shortcut patterns. We're saying, can we define cases that's short and minimal and do not have other weird patterns, so we can kind of say our model is addressing a single capability or not. And for example, say we want to know if our model understands important vocabularies or part-of-speech tags. The MFT would be simple. We just need some test cases and their labels. For example, this is a great flight is positive because of great. And maybe we can get 500 of those, and then we can run the model so we can get a failure rate on these test cases. Here is pretty much where we go back to the spirit of grouping. In a way, we are writing groups of test cases based on the capabilities and the expected label, so that the failure cases only reflects model's problem on this particular part. One cell can also contain multiple test definitions. We can easily write another test whose test cases are all neutral sentences to retrieve model's response to neutral questions or neutral sentences. Now we have 2 test cases. Can our model understand vocabulary? One focusing on more polarized words and the other one focusing on more unpolarized words. Another example with another cell, testing negation with negating sentences. And the other 2 types of tasks are perturbation tests, and they differ from MFT in 2 ways. First is, instead of creating examples from scratch, we're perturbing existing examples. And the second one is our expectations are not on explicit ground truth labels, but rather on the relations between predictions before and after the perturbation so that we can actually test model on unlabeled data. First one is invariance test. It's pretty apparent from the name that we're just expecting model predictions not to change. Here's an example for a named entity. When we are doing sentiment analysis, changing location name should not affect the model prediction. Like changing Chicago to Dallas or Brazil to Turkey should not make any difference. But in practice, 21% of such changes will trigger a different prediction. And finally, directional expectation test, just like invariance test, but we're not expecting variance. The example here is for testing vocabulary of a model. We can add at the end of every example a negative sentence like, "You're lame, I hate you, I dread you," and we can expect the sentiment not to go up. So whatever the sentiment was before, if I hate you, it should not become more positive. And this example is interesting because we are not constraining the labels, but only constraining the probability distribution of the labels. Such cases have a failure rate of almost 35%. So if you have this matrix, the process becomes pretty easy. It's very guided. You just fill the matrix up, trying to fill the cells of different tests. And in the end, you will get this test suite with pass and fails. And you can go and try to fix whatever failures you get. These tests can also be used repeatedly for other models as long as they're for the same task. So we mentioned before, you sometimes would want to write 500 examples for a particular test, and writing them from scratch seems to be a lot of work. But if we don't get to the number, or if we overly emphasize on certain words or patterns, the test coverage can become very low, and we won't discover interesting bugs. On the other hand, in perturbation tests, you get much more data once you finalize the perturbation function to, for example, change the flight destination. But the engineering effort required is pretty significant. So we try to provide a lot of tooling to make test generation at scale easier. This is the full list of functionalities in our toolkit, but I will only show you 2 fancy animations. And for the others, please check out our repo. The first one is to use templates to generate a large group of similarly formatted instances. That this one is, this is a blah movie, and to use masked language models like Roberta to get some creative suggestions on what to put in those templates. Eventually, checklist will save and expose them for you. Second one is to interactively inspect the test suite matrix. We start with a matrix summarizing the number of tests and failure rates per cell, and gradually dive into the full test list with respect to each capability. Here, like we mentioned before, we can see multiple tests in the cell of MFT negation, and it contains very simple ones like it was not good, and also more complex ones like I thought it was good, but it was not. And we can clearly see how the model reacts differently to different patterns, with the failure rate going as low as 2% and as high as 98%. Further down, we see details in each test, like their test type, capability, their design, and the actual test cases involved. And this is one of the hard MFT on negation. It tests whether the model can correctly ignore the neutral clauses. Examples are like, I wouldn't say that the food was extraordinary, with given that I'm from Brazil in the middle. We expect the prediction to be negative, but it's actually positive. And the total failure rate is like 74%. Now, when we shared the idea of checklist in earlier days, our colleagues and friends were like, this is too simple. Models nowadays are good and they're gonna pass. So it did some case study and user study with different user groups to see if checklists can help find bugs in commercial models and state-of-the-art research models. Here I will give some more examples on our running story, the classic sentiment analysis. We tried 3 commercial services sold by Google, Microsoft, and Amazon, and also two research models, BERT and Roberta. We use the Twitter data, which is a scenario that all of the commercial models claimed to support. First one we see is if an invariance is an invariance on vocabulary, and we use BERT to perturb some neutral stop words and expect the prediction to remain like this. This is a very simple test, and even for all of the other tests that I will give you, we did not try to trick the model with adversarials, and we only use cases that we thought the model should handle. But both Google and Amazon models would have pretty high failure rate. And a directional one we've mentioned, adding negation sentences should not make the prediction more positive. But Google has a 35% failure rate. And robustness, we hope the model does not get confused by irrelevant changes or typos, but even just randomly adding a fake URL or username, almost all of the models would fail for 10 to 20% of the time. And some capabilities down here would require some creativity. If we care about temporal changes, we can create a MFD with examples like, I used to love it and now I hate it, and so on. It's a pretty hard test, but all of the commercial models fail more significantly, up to 30-something%. Simple negation, it wasn't a lousy customer service. Google fails more than half of the time. And do I think this company is bad? No. Almost all of the models would fail on questions and answers. We also did case studies with Microsoft's sentiment analysis team. This is a team that trained the model we were testing before. And the team has been stress testing this model, so they know a lot more about the model than maybe any general user. And we wanted to know if checklists do bring some values to them. And so we had this 5-hour session with the team that built the model. Even for a stress tested model, the tool is pretty useful. And they tested capabilities they have not considered, and also capabilities they have considered, but not really in the way that we presented. And even capabilities they have benchmarks were tested more thoroughly and systematically with checklists. They discovered many previously unknown bugs, and they told us they will fix it in the next iteration. We will see. We also tested other tasks and models with exactly the same matrix and the same process. With same tests on different models, checklists also help with model comparison. And we can easily see even state-of-the-art models still display many bugs. So it's a matrix design based on the software engineering principles. We tell people what to test. And here's a list of capabilities and also how to test with a list of test types. And we also have tooling to help scaling up the test. But once we have these bugs, the next thing for us to know is, so what? And so for next step, we hope to research more on how to actually fix the bugs. We find like either through data augmentation or using perturbation functions as feedback to the model training process could help to some extent. And I can explain this a little bit in the next project. Polyjuice. Polyjuice is really trying to do perturbation. And if we draw the human machine axis for doing perturbations, we see automatic methods have some limited patterns, and manual rewrites are pretty costly, and rewrite functions would require some domain expertise. And they're also still tedious because just one linguistic pattern like negation can need dozens of templates for rules to enumerate. And that's why we have multiple different test cells and checklist. And in this work, we try to automatically produce interesting counterfactuals by making it a natural language generation task. While most language models are usually used to complete some paragraphs, we fine-tune them such that when we give the model a phrase or a sentence, it does not try to elaborate, but instead it tries to rewrite things. This way, we naturally will get some diversities from models like GPT-2, but we also designed the prompts to allow more targeted counterfactuals. So instead of enumerating all of the negation patterns, we can just say like add negation modifiers to auxiliary verbs. For how to change, we designed control codes based on a survey on existing papers doing counterfactuals. The codes tries to range from very concrete changes like negation, quantifier, or shuffling to more loose ones like you can replace words or replace prepositions, and distinguishing, adding, removing, and replacing some subphrases or restructuring. Certainly, there's no existing data set that can just naturally give us all of these control codes, but we can easily merge existing NLP data sets with paired sentences to get a pretty fair coverage on all of these control codes. We further add this fill in a blank structure. Intuitively, for each pair, we try to start with the original sentence to always provide the context of what you're changing from, and denote the rewriting part with a specific token, and also how to perturb. Then for the new sentence, we blank the places changed and add the supposed answer to the end. So if we use all of these as the prompt, the model can fill in a blank by generating this part. And to make more flexible blanking, we also cover related parsing trees like not to is not, all the way to blanking the full sentence as if there's no fill-ins or as if the model is fill in everything. And eventually we will get 650K training prompts. When we get a bunch of counterfactuals from the model, we can then filter or rank them for different downstream tasks. And I will give you two major applications. First is to address the so what question in checklist through some counterfactual data augmentation. We select some diverse change patterns to touch different decision boundaries, and then task Amazon Mechanical Turk workers to label their validity and also cross-label. And we did it for 3 tasks. For system analysis, compared to just adding the same amount of original data, we improved the model on Twitter data sets and contrast sets, which are human-generated counterfactuals from prior papers. And similarly for NLI data, where we try to determine if the premise sentence entails or contradicts with the hypothesis sentence, we improved on contrast sets and challenge sets. And in fact, the improvement is compatible or sometimes even better compared to augmenting with manual counterfactuals. But this only happens for targeted augmentation. And actually, we hardly saw anything if we just do random data augmentation. And I suspect it's because there are many patterns that are already learned by the model or learned by the pre-training. And we benefit more if we only target at its error patterns. And compared to the reported time for humans generating counterfactuals, we can be more effective because Turkers only need to verify new changes instead of writing them, and they get to label multiple related sentences together so they can focus on the changed part without having to reparse the entire sentence every time they see a sentence. And we also look at how the generated perturbations help with model explanation and analysis. Let's start with an example. Say we want to understand a duplicate question detection model, and it says these 2 questions are the same. And now we apply SHAP, one of the state-of-the-art explanation methods, to get the importance distribution across the sentence. What do we learn? We probably would notice that the model would focus in depression a lot more, but would ignore this part like a friend who is blah, blah, blah. So we would expect the model to go wrong if we change the first half, but would correctly predict non-duplicate if we change in depression to something else. But ignore the first part is pretty abstract and it's not as understandable as a counterfactual. Like if you change help in the second question to find, the model will still say the 2 questions are duplicate. Or more severely, It can also give you a false signal on what's correct and what's incorrect. It's surprising that when you change the not important friend to woman, the model would still say not duplicate, or that it will still say duplicate when you change in depression to suicidal. And the reason behind this is SHAP or LIME, it estimates feature attributions essentially through masking or deletion. So there are many points that could reflect more natural counterfactuals like changing friend to women. That's not masking, and they could have tuned the local decision boundary more precisely, but they didn't because they're not used. So we want to use these natural counterfactuals to complement observations from feature attribution methods. And more concretely, we select surprising counterfactuals or those that violates the expectations set by SHAP. And this would include examples where the real change in prediction is pretty large, even though the importance score computed by SHAP is really low. Or examples where the prediction does not change even when the importance score is really high. And in a user study, even after seeing original examples, the SHAP explanation and manually doing their own perturbation for like 10 times, NLP PhD students still cannot really simulate model behaviors on the Polyjuice generated surprising counterfactuals. In fact, they do not do much better than random guess. And this means indeed Polyjuice counterfactuals complement feature attribution explanations by displaying some information that we would miss even after we have manually explored the model behavior beyond just explanation. Besides analyzing counterfactuals on one particular instance, generating multiple counterfactuals for multiple instances is also interesting. And this is where we go back to error analysis and make a cycle with Erudite. Let's try to inspect a natural language inference model. And there is a known correlation between the label contradiction and hypothesis with negation in NLI datasets, which cause the model to fail on a lot of non-contradiction negations. We can try to rebut this by randomly select a neutral premise and hypothesis pair. A woman is holding a baby by the window does not have any indication on this woman is looking at the window. And we can generate multiple counterfactuals on it based on the control code negation. We would expect that after the negation, the ground truth answer should still be neutral, but instead for no woman and isn't looking, here the prediction becomes contradiction. We also quickly see this inconsistency between is not and isn't. And this is something we would not notice in most of the manual counterfactual analysis, because usually once you tested it's not, you would expect isn't to just work the same way, but it does not work the same way. And we wanted to know if the pattern generalized. We can easily just generate counterfactuals for many other neutral instances and then extract them into frequent perturbation templates and see how many times this would make the neutral prediction flip to contradiction. We can see that the prediction flips much more when we change a determiner to no. And so there's probably more nuances in this correlation observation than we originally thought. Going back to the two building blocks, Polyjuice obviously focused much more on perturbation, but also offers some support to grouping. So yeah, that's pretty much the three work I wanted to talk about. And on top of Polyjuice, we still have some ongoing extensions, including some direct follow-up on better generators and interactions with generators, and how to extend structures and grouping from analyzing existing data to collecting new data. I can talk a little bit about this, or we can directly go to questions depending on what people want.
If no one else has a preference, I'll say go for it.
Cool. Yeah, I will be really quick. So first, better generator. We will have a better name, but it's Polyjuice 2.0. So Polyjuice is broadly applicable for different applications, but it's also not bias-free because the control codes are predefined and not really exhaustive, and the model is fine-tuned on paired data sets. So some perturbations are more likely than others. So our next goal is to build models that can achieve controls without really relying on paired data sets or heuristic control codes. And at a really high level, what we do is to instead try to rely on more well-defined linguistic features from tasks like semantic role labeling or dependency tree parsing. So the model can figure out roughly what to fill in and where using all of these linguistic patterns that's established by linguistics. For example, with the label being manner from SRL, the model would only fill in the last blank with a good guy, versus temporal tag would drive the model to generate through a 13 months period in the middle. And also the generator can take some more content level control. So in this very last example, if we explicitly ask it to include the word profit in the location modifier, the model would do add a perfect profit. And then second, from a more HCI perspective, we're also exploring how people would interact with Polyjuice or also other large language models like GPT-3. Like generators are obviously more scalable, but only humans know what they want. So I'm interested in seeing how different levels of human involvement change the final perturbation produced by the human generator team. Third one is to provide valuable groupings and counterfactual reasoning at the time of capture, such that they are part of the data set rather than we just adding them after we already create the data set. And the key here is really to do grouping using the counterfactuals. And for example, in this case, removing negations almost always result in a different class label in sentiment analysis. And we can easily infer that there's an impact on negating the sentences and can then try to group them together. But yeah, that's pretty much the line of the work. And with the knowledge from the analysis, I hope we can eventually build better models and answer questions like, when is our model ready for deployment? Where do we need to improve them and how to achieve the needed improvements? And thanks.